parameters of the fed codes are the ones shown here. The number of data packets that are used at each step, the number of packets that are generated to protect those original packets, which is called the redundancy, the total number of packets that are sent to the network, and two more parameters that are used to measure how much redundancy is added. So there is a great variety of alphabet codes, which very much differ in terms of in terms of the performance they can give regarding latency, effectiveness, or efficiency. So the one to select depends on the scenario, on the service that we want to provide. So in the one we are focusing on, the real transmission of multimedia content, the Pro and POP3 codes are very well appreciated and widely deployed, alone or with other, jointly with other codes like Raptor, because they are very effective against error bars. They are of low complexity regarding both how they are organized and the operations that are performed, and they are very good. They are very efficient and effective at low packet loss rates. However, they start performing worse as channel conditions worsen. So, as a main observation, this thesis explores strategies to improve the performance of these codes. We do so by generalizing and optimization how they work without compromising their very nature. So now I'm going to explain how these standard POP3 codes work. So first we have the encoding procedure in which we will select K packets out of the stream and arrange them in one single packet of L columns and D rows in the following way. So the first packet in the stream will be arranged in the first row, first column position, second one in the second column of the first row, and so on, so on, so on, until we're done with one row, and we'll start with the next one. So at the end we will have D times L packets arranged in the matrix, and the possibility to create repair packets column-wise, both row-wise, or both ways. The creation of these repair packets is the result of applying an XOR operation over several data packets. So in the end, POP3 codes are not more than a combination of simple XOR codes. What is characteristic of these codes is that they can only recover up to one data loss out of the number of packets that were used to create this repair packet. So through this we can easily see that the packets that can be created row-wise can be work very well with independent packet losses, and the column-wise generated packets with error bars. And of course, these POP3 codes will fail when these situations don't work. So if we generate the packets column-wise, if we have more than one lost packet in one column, that cannot be recovered from. The same happens with the row-wise generated packets. If we have two packets in the same row, this cannot be recovered, or a combination of the two if both dimensions are used. So, as I said, we have these three types of configurations, so row-wise only, column-wise only, or both ways. Selecting one over the other will depend on the scenario that we're facing, because all of them have different pros and cons in terms of latency, and the overhead, and recovery capability. And now a word about the dimensions of the matrices, which actually very much define the capability that they have to recover from losses, in the sense that, for example, if we have a column row-wise generated packet, if the number of rows that are used in this matrix define the error recovery capability of these repair packets in the sense that the low if it's less likely that we have more than one lost packet in this column. So the number of columns and the number of rows will make these packets, these repair packets, more or less reliable. So as I said before, the main drawback of these top-3 codes is that they become less and less efficient as channel conditions grow less favorable. And so we have introduced a new equal error protection extension to them, which basically allows the introduction of a new dimension, a third dimension for protection. Introduction of third dimension doesn't mean to introduce extra recovery packets, but only the possibility to generate more different combinations of protection, so that they can better adapt to the conditions of the scenario we're facing. So this can be formalized in the following way. So first, we can describe actually the standard dimensions of the codes, of the standard codes, by using these two parameters, n and g. N will be the number of packets that are used to generate one single packet, and j the number of also the gap, the sequence number gap between two consecutive packets that are used to generate that repair packet. So, for instance, in the row-wise generated case, that will mean n equal to L, which is the number of columns, and j equal to 1, as the data packets that are used to generate that packet are subsequent in the data stream. And for column-wise generated packets, that will mean n equal to d, the number of rows, and j equal to L, the number of columns. So for this new third dimension, we'll use these numbers n and g sub 3, which can take whichever number we want, only if they meet the condition that is expressed there, which is imposed so that to guarantee that all the data packets that are used to generate redundancy of this third dimension are within the effect block and not before or after that. So we will evaluate this introduced extension through simulating the transmission of data packets over an unreliable channel. And we will do that by using two different channel models: the random model, which will introduce independent losses, and the rain model, which models actually the main source of error of DS